Okay, part 2 of chapter 4. So here we're going to talk about the octet rule, and we're going to start by looking at what we call the Lewis structure model. So this is going to be representing our valence electrons. Our valence electrons are the outer shell electrons, and we're going to represent them using what we call electron dot structures. Okay, so for example, oxygen has 6 valence electrons. And I'll show you where that comes from here shortly. But knowing that it has 6 valence electrons, I'm going to represent that with 6 dots around the elemental symbol for oxygen. Now, depending on, I'm just going to say X is our element, even though it's not really an element. We can have a total of 8 electrons shown around our element. And those happen, there's 2 on each side. Okay, so you can at max represent 2 electrons on each side. When I go to fill my electrons, or let's actually talk about oxygen, you do one at a time, and one at a time without pairing. So I got 1, 2, 3, 4. Now I have to start pairing. 5, 6. So oxygen, it's a Lewis dot structure, has 6 valence electrons. 2 of them are paired and 2 of them are not. Okay. The valence electrons, like I said, are the electrons in the outer shell. So this is where like your electron configurations come into play. However, it's actually pretty simple. So all of your atoms in group 1, so this is sodium, potassium, lithium, your whole group 1 on your periodic table. So go ahead and take out your periodic table. All of those have 1 valence electron. So in that group, we have sodium. Group 1 has 1 valence electron. And we just represent it with 1. Group 2, where you find calcium, group 2 has 2 valence electrons. Okay. Group 3, where you find aluminum, group 3 has 3 valence electrons. Group 4, where you find carbon, has 4 valence electrons. Group 5, where you find nitrogen, has 5 valence electrons. Group 6, where you find oxygen, has 6 valence electrons. And group 7, where you find your halogens, has 7 valence electrons. So fluorine, chlorine, etc. So again, these are your outer shell electrons, outer shell meaning the ones that fall in the outer shell. These are super important because these are actually the electrons that play a part in bonding and reacting. So understanding them is essential. All right, now moving on, let's talk about the octet rule. One thing I didn't tell you before is that I didn't talk about group 8. Group 8, where your noble gases are. Neon. Oh, let me do that again. Neon. Group 8 has 8 valence electrons, with the exception to helium, because it actually only has 2 electrons. But everything else in group 8 has 8 valence electrons. This is ideal. This is actually the goal. The goal is when I get 2 atoms that come together to form a bond, that they go from having a certain number of valence electrons to having 8. We call this the noble gas-like configuration. It's the most stable state that we can have, and this is the goal. And to get to that goal, our atoms are going to either gain, lose, or share electrons in order to get to 8. All right, there are exceptions to the octet rule. One of them is they can have expanded octets, so they can have more than 8. We'll talk about those later on. This only involves elements that are in period 3 or higher. So period 3, 4, 5, and so forth. A couple other exceptions to the octet rule are hydrogen, lithium, beryllium, and boron do not follow the typical octet rule because they can't have 8. They're going to get to be like helium. So helium only has 2 electrons. It's a noble gas, and those 2 electrons are going to be paired. That seems different, and it is, but we want to get all our elements to be like the noble gases. And lithium, hydrogen, helium, beryllium, and boron, they don't have the ability to get 8, but they certainly can get to 2 by losing, gaining, or sharing electrons. Lithium will lose 1 to get like helium. Hydrogen can share or gain an electron to get like helium. Beryllium will lose, and when it loses 2 electrons, it becomes this beryllium ion with a 2+ charge. Boron will lose 3 electrons to become this boron ion, and that'll end up giving it a configuration like helium. Okay, so let's do this. Let's write the Lewis dot structure for calcium and chlorine. Calcium is in group 2, so it has 2 valence electrons. So here's 1, here's 2. Chloride, or chlorine, has 7 valence electrons. So it has 7 here. Okay. If I want to put these 2 together to make a compound, and that compound is actually going to be calcium chloride. Before I do that, I'm going to go ahead and go over here and talk about, for an example, sodium. Oh, let me not worry about that yet. And chloride. Sodium has 1 valence electron. Chloride has 7. Okay. Now, if I want to bring these 2 together, I know that when they come together, because this is a metal and this is a nonmetal, I'm going to be losing and gaining electrons. The metal's going to lose, and it's going to lose 1. And the nonmetal is going to gain, and it's going to gain 1. Why 1? Because chloride has 7 valence electrons, it wants 8. So when sodium loses its 1 valence electron, it takes on a +1 charge. And when chloride takes that electron from sodium, it gains it, it takes on a -1 charge. And now, because these 2 charges are equal to each other, we can just put it together. NaCl. So you bring them together, sodium and chloride are held together by an ionic bond, and that would be its chemical formula. So let's go over here. Calcium and chloride. Calcium's a metal, chloride's a nonmetal. So I know this is going to be held together by an ionic compound, or an ionic bond. Calcium's in group 2, has 2 valence electrons. It's going to lose 2 electrons. And it's going to take on a +2 charge. Everything in group 2 will take on a +2 charge. Chloride, we already discussed, is going to gain 1 electron to get to 8, so it takes on a -1 charge. So now I have calcium with a 2+ charge and chloride with a -1 charge. Can I just put those together like we did here? No, because we need these charges to balance out. So actually what I need is 1 more chloride. Now can I? Sure. I have 2 positive here, 2 negative here. So I would write that as calcium chloride. 2 chlorides, I'm going to write that as a subscript. So 1 calcium to every 2 chlorides. All right. So the Lewis theory predicts the number of electrons a metal atom should lose or a non-metal atom should gain in order to make a stable electron arrangement. This is your octet rule. Right, so I'm going to go over it again. Go ahead and get your periodic table out. Group 1 is a metal. It's going to lose 1 electron. Therefore, all the metals in group 1, like sodium, will take on a +1 charge. All right, group 2 metals are going to lose, these ones are going to lose 2 electrons. They're 2 valence electrons, like calcium. And when they become that ion, they're going to take on a +2 charge. Group 3, the only one that is consistent is aluminum. So next to aluminum, right? Aluminum has 3 valence electrons. It's a metal. It's going to lose 3 valence electrons, so it will take on, when it's an ion, become a +3 charge. Group 4, we're just going to skip. It's not going to take on a charge. Group 5, where we have nitrogen. Nitrogen has 5 valence electrons, right? It's going to gain 3 because it's gaining because it's a nonmetal. So nitrogen and phosphorus, your nonmetals, when they're an ion, are going to take on a -3 charge. Oxygen, group 6, it has 6 valence electrons. It's going to take on 2, gain 2. So your group 6 nonmetals, when they're ions, will have a -2 charge. Group 7, your halogens, like fluorine, has 7 valence electrons. It's going to gain 1. It's gaining because it's a nonmetal. And therefore, when it does that and becomes an ion, the halogens will take on a -1 charge. Okay. I'm actually going to skip through this. All right. So keeping the talk about ions, let's talk real quick about conductivity. So ions actually can conduct electricity. And what I mean by this is, all right, so sodium chloride. Sodium chloride is made up of a sodium ion and a chloride ion. When they're put together as a solid, that's what it looks like. Ions, when they're in ionic form, so they're separated, they're not together as a compound, they can conduct electricity and actually light up a light bulb. These are called our electrolytes, and we will come back to them a little bit later. All right, so let's look at the writing an ionic compound. Let's look at what we just learned. All right, so write the formula for the ionic compound that forms between calcium and oxygen. Calcium's in group 2. So as an ion, calcium is going to have a +2 charge. Oxygen is in group 6. As an ion, it's going to have a -2 charge. Can I just put these two together so it's 1 on 1? The answer is yes, because those charges balance out. All of our ionic compounds are going to be neutral at the end. Okay. Now let's look at putting aluminum and nitrogen together. So aluminum is in group 3, and it has a 3+ charge. Nitrogen is in group 5, and it has a 3 minus charge. So if I put these two together, I can just put 1 on 1 because it balances out. So I have AlN. That would be the ionic compound. Let's talk about naming them. Okay, so first of all, again, ionic compounds are metal plus a nonmetal. And how we're going to name them is the metal is always written first, and it will hold the name of its element. The nonmetal is always written second, and it will end in "ide."
Okay, I was over